Right to start. Okay, thank you very much for being on time. It's about time to start this session. I will start saying that it's my pleasure and privilege to introduce my very best friend and very best collaborator, Professor Henrik Lund, a Danish engineer, well known to many people here, Professor in Energy Planning at Aalborg University in Denmark. He has done a lot of things, I would say some important things. During his time in Sustainable Energy Planning, research group at Aalborg University has grown to approximately 30 staff members, including 4 professors. Henrik Lund is the editor-in-chief of Elsevier's high-impact journal Energy, with annual more than 11 or 12,000 submissions. We'll see this year how much we'll get. Henrik Lund is the author of more than 400 books and articles, including the book Renewable Energy Systems. He's the architect behind the Advanced Energy Systems Analysis Software Energy Plan, which is a freelance used worldwide that used worldwide that have the form of a basis of more than 200 peer-reviewed journal papers around the world. So it's our pleasure to listen to Henrik and delivering this important subject on renewable energy systems and decarbonization, and especially smart energy systems. Thank you, Henrik.
Yes, thank you very much, both for the kind invitation to be here today and also for the very kind introduction. It's always a pleasure making a speech at the SDEWES conferences. Last year when we had the SDEWES conference in Dubrovnik, I did make a small opening speech, small contribution during the opening ceremony. And now this year it's the anniversary, 20 years, but I was a little premature already last year. I looked a little back into the conferences during the open ceremony and sort of looked at what have we been discussing during the SDEWES conferences. And from the very beginning in 2002, where I participated in the very first conference, we of course discussed a lot of things, but we also discussed renewable energy. Then later on we started, I believe, as sort of a first mover during these conferences here to put on the agenda the 100% renewable energy systems as a target to head for, and also something that we as researchers would give a contribution on how we could do and how we could put together. We also made a lot of different things looking into smart energy systems and a lot of other things. My point last year was that we have been looking a lot into and maybe many of you have been looking a lot into energy and maybe energy and transport systems, but if we listen to what our politicians is wording it now at what are the targets, then they use words such as zero emission or carbon neutral and all the sort of things. And this means that us who have been looking at the 100% renewable energy systems, we should have a broader look, because we also have to coordinate ourselves or even include also other sectors that have greenhouse gas emissions, even if they are not the energy or the transport sectors. And that's what I sort of put on the opening speech last year. And what I'll do this year is sort of then elaborate more and also show a little bit of how we can do that, and also what this means to how we should be thinking when we, as I do, talk a lot about 100% renewable energy system. And that's why the title is Smart Renewable Energy Systems and a Fully Decarbonized Society. So that's what I will try to say more about now. First, I will say that parts of what I'm saying here is, of course, published in my book. Already in 2014, the second edition, I elaborated a lot on the smart energy systems approach and context, and that will be part of it here. But I will update not only what I've been writing before, but also what have happened since, especially with a look at the climate neutral targets. And just as an example, this is taken from the European A Clean Planet for All report they issued a couple of years ago, and they use this word climate neutral, and they also look not only at the energy sector, but much broader than that. And when we have politicians looking into this type of goals and targets, then I think it's our contribution from the scientific part of view and also from the industry somehow to say how can we do this, because it can be done in many ways. And no matter if we word it 100% renewable energy or climate neutral economy or how we put the words, then there are different ways of doing it. And what I'm sort of in, and I believe many of you also, we are in the business of identifying the best, the most doable, and the most affordable ways of making this green transition, both from technical point of view, but also from an economical point of view, and also from a road mapping political point of view. How can we do this, and how can we work as researchers in order to identify the best and most affordable and most doable ways of doing it. And the way we work with this in my research group, and I guess many others do in principle the same, this is sort of to put our energy systems into computer models and then play around with, now if we build a lot of wind turbines, what will happen and how can we deal with that, and many of the other things. And that is also what we do at Aalborg University with this model here that is a freeware already mentioned by Soteris. So please download and play with it if you wish. When we talk about smart energy systems, and I will elaborate a little bit on that, because this is our suggestion to an approach to take if we should organize ourselves so we will be doable for us and possible for us to identify the best ways. Then I always start with saying a little bit about smart grid, because the reason why I and others started promoting the concept of a smart energy system is because we once had this smart grid popping up. The earliest mention of that I could identify when I was looking into it, was this paper from 2005 where the concept of smart grid is mentioned. And what is said here in this paper is now we have invented a computer and the ability of being smart and making smart control of what we do, why not use it? And then they look at the power sector. We can use it in the consumption to be smarter there. We can use it in the distribution and the transmission and also the generation of electricity. And that's what they sort of promote. So let's be smart. Let's be smart grid. The problem with it, as I looked into it, was there was not really a scientific definition in this paper here. And when I was looking for a scientific definition, what is smart grid, then I couldn't, in the beginning, find anyone. What I could find was non-scientists, like organizations like the DOE in Washington, or the International Energy Agency, or the European Commission, and so on. They started to define what smart grid is and put down definitions. But these were not really scientific definitions in the sense that the reason why they did this was because they started granting money for it. And then they had to define what they were granting this money for. And that's where we had the first definition of what a smart grid actually was. And when I took a look at all these definitions, well, they didn't agree 100% on what it was, but there were some similarities, you can say. And one of the similarities was that they were only looking at the electricity grid and not the rest of the energy system. And that's only, as all of us in this room know, that's a minor part of the complete energy system, and therefore also a minor part of the green transition. And this is why in the book here and also in other papers, we set out to have a more scientific definition. So we defined, and then I defined not smart grid, but smart electricity grid. And then I could also see that there were also people within the district heating sector and district cooling sector that started in the European Commission to define other types of smart grids, thermal smart grids, and I've then defined that here. And also we included the smart gas grids and then put down something that is our contribution to what could be the scientific definition of what it is. But the point we tried to make by doing this is that if we really wish to be really smart, then we should not be smart within the different grids and in the different subsectors. We should be smart across the subsectors, and that's how we define the concept of smart energy system, that is taking a cross-sectoral approach to be smart and also identify the synergies between the sectors. We published a review paper about that some years ago. It's where we can see that its concepts have sort of been implemented and used in a number of papers since, even though there still seem always to be some discussion on what exactly are we talking about and what is the definition. But at least this is sort of developing itself in a direction where we agree more and more upon that. But what is a smart energy system? You can say it's an approach to identify the best and most affordable solution. It's sort of a guideline. If you wish to really do this good and be smart, then how should you do it? You can even say it's a theory, because when we promote this and I talk about it, I sort of make the theoretical statement that if you wish to identify the best and most affordable solution to the green transition, you must take a cross-sectoral approach. You must take a holistic smart energy system approach. Otherwise, you'll push yourself into some corners of the whole problem and identify suboptimal solutions. So that's the idea about this. And basically, the idea is to sort of recognize that the different subsectors and different smart grids, they need one another in order to find the best solution. You can say that it's very difficult to green the heating sector without some kind of input from the electricity, heat pumps and the like, and also excess heat from different processes and production. That is the most affordable and best way to green the heating sector. And maybe you cannot do it without certain inputs from the electricity sector. So the electricity sector will have to help the heating sector. Also, the electricity sector will have to sort of assist the transport, because we should have electric cars, but not only that, also all kinds of power to X to deal with sustainable aviation and things like that. So we also need the electricity sector to assist the transport sector. But then in return, the transport sector and the heating sector can make a very important contribution to the electricity sector, and that is in the balancing of wind and PV. Because if we recognize we have to convert some of that electricity into heat or gas or liquid fuel or whatever we need in the other sectors, then we also have the possibility of storing all the fluctuating wind and PV after it has been converted into something that is much more storable and affordable to store, rather than try to store it while being an electricity consumption or electricity production. And that's sort of what we have designed our tools to be able to do. That is to take all sectors in and make hourly calculations of all the sectors, and also to include as many conversion units as possible and various types of storing, so that we can play around with. Can we design this? Can we identify those synergies? And can we design a system so we can do with the affordable technologies and don't corner ourselves into being forced to invest in the very expensive technologies. That's sort of the game. And one of the reasons why this is incredibly important, and also one of the reasons why, if you take this approach, you will be able to identify better solutions than if you don't. One of the major reasons is that there is really a big and huge difference between the cost if we try to store energy as electricity, and I define electricity storage as you put electricity in and 1 hour, and then later you take electricity out. It could be a lot of technologies, of course, batteries. It could be, as illustrated here, pumped hydro. It could be converting to hydrogen and back. It could be many different technologies. We don't have mountains in Denmark, I often say, so we cannot use pumped hydro, but we can use compressed air energy storage instead, and so on. There are many technologies, but in common for all these technologies is that they are in the order of magnitude 100 times more expensive than building a thermal storage. And this is here illustrated with a big tank of hot water and sometimes cold water in a small district heating system in Denmark. And thermal storage is again 10 times more expensive than a gas storage, and a gas storage is again 10 times more expensive than a liquid fuel storage. And liquid fuel in the future could be in methanol or some kind of green liquid fuel. And this diagram here, or this cost relation, are important because if we can design a system in which we do not really need a lot of electricity storage, then that system will be so much more affordable compared to if we can't. And that's why this is important. This paper here document all the numbers I just used before. Then there's another reason, and that other reason is that we already have a lot of storage. This diagram here illustrates the storage capacity we have in Denmark right now, and we have a lot of oil tanks, but in the future we could put something, other type of liquid fuel into them if we wish. We also have a lot of gas storage. And then I also try to illustrate here in the little red dot the thermal storage we have. We have quite a lot of thermal storage in Denmark because all of our district heating pipes are thermal storage in itself. We have a lot of also seasonal thermal storage capacity, and we also have all the water tanks in all the houses. So they are sort of summarized into this diagram here. I haven't shown our electricity storage because it is so little that it cannot really be there. But the point I try to make by showing this diagram here is that we already have a lot of storage capacity. Very often we tell ourselves, now going into the future with all this fluctuating energy from wind turbines and PV and so on, we need a lot of storage. But I'll sometimes say a little bit back, maybe we do not need a lot of storage because we have a lot of storage already. What we really need is access to the storage. And we calculated, just to illustrate one example here, this is a scenario 2050 with 100% renewable energy in Denmark. And as you can see, we can more or less deal with the storage we have if we organize it in a way so we don't try to store the wind and the PV in electricity storage. That is very expensive, but we do it by converting it. So we have added some hydrogen storage here. It doesn't look like a lot when we compare it to our existing natural gas storage, but it is actually a lot of hydrogen storage here. But it's only for temporary storing. It's for expanding the electrolyzer's capacity beyond what we need if they were operating 24/7. But then we can operate them to better balance the wind and the PV, and then we have to store the hydrogen until we, as we suggest, we put some carbon to the hydrogen and end up with some methane we can store in our natural gas storage, or some methanol, or even something we can do for aviation that we can store in our oil tanks. And when we do this, the only electricity storage we have is actually the one for the electric vehicles. And as you can see on this illustration, it's very small compared to all the other types of storage we need in the system. And this is a system that we have calculated hour by hour in all sectors, 100% renewable energy in 2050 for the case of Denmark, where we can document how all storage are filled and empty and all this sort of things, so we can document this can work with this storage as you see it here. And that's good news, because this means that we don't have to really invest in a lot of electricity storage. And that's good news because they are so expensive. Then one more reason why taking a smart energy systems approach is important is also if we take a look at the grids we have. And sometimes I make a competition, especially when I'm in Denmark, I ask people, what do you believe the energy we distribute in Denmark, do we distribute the most on the electricity grid or on our district heating grids or in our natural gas grids? And very often people have the opinion it must be the electricity grid that is the most important, that distribute most. And that's why I made this diagram here, because that's not the case in most countries, especially not in Denmark. I mean, if we take this is a proven peak hour distribution of energy in our grids. And as you can see, we have distributed twice as much in our district heating grids as we have ever done in our electricity system. The same for natural gas. And the idea of showing these numbers here is that sometimes we live in the, I will say, illusion, or we live at least in the idea that we should electrify everything and put everything onto the electricity grid, both the heating and the transport and so on. But if we do that, we really need to expand our grid. And we calculated once, if we put everything, just everything from the heating sector onto electricity, that would say converted everything in Denmark into electric heating. Then we would have to build a lot of wind turbines in order to supply that, and that would cost a lot of money. But then we also calculated what will the cost of the grid be to do that. And the cost of the grid exceeded the cost of the wind turbines, because to expand the distribution grid in Denmark like a factor 4 will be extremely expensive. And then we also calculated, but if we do this and we also then need electricity storage, then the cost of the electricity storage exceeded the cost of the grid that exceeded the cost of the wind turbines. So the idea here is to say that we already have some infrastructure ready. And of course we should electrify a lot. We should have electric cars and also electrolyzers and a lot of things. But there's no need to overdo it, because if we overdo it on the distribution level, then it will really cost a lot of money. But if we do not overdo it and make use of the existing infrastructure and then add to that more on the transmission level, and the transmission level is so much more affordable to increase than the distribution level, then this is doable. So these three things here with the infrastructure of the grids, the infrastructure of the storages, and the cost of the storage, this is just to illustrate why taking this holistic approach is so incredibly important. I'll say a little bit about district heating also, because in Denmark we are crazy with district heating. We have a lot of district heating. Half of our buildings is supplied from district heating, and we have been discussing with ourselves, should we have district heating in the future or not? Because it's really been fantastic, because we have been able to recycle all the excess heat from electricity production and then heat our houses with it, and saved a lot of fuels. And today we are very, very happy about it, because we have very few natural gas boilers left in the system. Most of our houses are are heated with district heating. And our district heating companies in Denmark have not increased the price, only a few of them. Most of them, 90%, have not increased prices of heating our houses in Denmark during this period of where gas prices and electricity prices have increased. Some of them have made a huge profit because some of them supply heat from waste incineration that also produce electricity. And producing electricity on waste right now is a really, really good business. And then they can even lower sometimes the heating rates. Then of course other things also increase. So, but basically it's not an issue. So right now all people who have a gas boiler in Denmark, or oil boiler for that matter, or electric heating for that matter, they are calling their local district heating company and want to be part of the district heating supply. And all district heating companies in Denmark are expanding as fast as possible, but still it will take them several years to put all the rest customers into the systems. And then you can say, is this stupid? Because one of the reasons that we have so much district heating and have so much success about it is that we have been producing our electricity on steam turbines produced on coal and whatever. And this is not something we should do in the future, because in the future we should replace these coal-fired power stations with wind and PV. But from what we see, there will still be, or there will be even more excess heat in the future. And we have sort of looked into in Denmark, if we look at what we have of industrial excess heat potential that we are not already using. And even though we electrify some of them or put them to biofuels or whatever, we will still have a huge potential in the industry. We also looked into the expansion of data warehouses in Denmark right now, and we're expanding them so fast that if we succeed, then in a few years, the potential excess heat from our hyperscale data centers in Denmark will be equal to 1/4 of our district heating demand, quite a lot. And then we also have potentials for geothermal energy, and it's actually both in Aarhus and now also in our capital, Copenhagen. It just signed a contract to go for that. And then the final thing that is also important here, and I'll come back to that, is in this future where we should also have power to X electrolyzers and biomass conversion and all these things that go within the concept of what we call power to X, there will also be a lot of waste heat, and that's also being expanded and being, organized in a way so we can use the excess heat from that. So as far as we can see, when we sum up all this in the Danish case, we put those four things together, then the sum of that potential for the future is actually more or less equal to the total heating demand of our future district heating system, even though we expand them. But then, of course, you cannot utilize all of it because it needs to be in the right spot at the right time, and there's winter and summer and geographical issues. But what we think is realistic, that is to use half of it. And then the rest will be heat pumps and waste incineration and maybe also some peak load power stations and solar thermal and whatever. So for that reason, we really see that district heating is essential. And we have also been promoting also what we call the fourth generation district heating technologies. That is where we realize that in the future, it will really be beneficial for us if we can decrease both the supply and return temperatures of district heating for various reasons. One is not to have so many losses in the grid, but that's not the really important thing. The really important thing is that the sources for providing district heating in the future, no matter if it's a heat pump or it's one of the many resources I just mentioned here, geothermal energy, waste, whatever, then we can do so much better if they are allowed to deliver at a lower temperature compared to what they are now. So that's what we promote as the fourth generation district heating technologies. And we also been promoting this on the European scale, and actually in the European roadmap studies, there are 4 of them now, shown how it will be both more affordable and doable to implement the political goals in Europe if we include district heating compared to if we do not include district heating. And we also aligned that with what we call Smart Energy Europe, a study where we have looked at the whole of Europe, and we also looked upon it at the city level. But what I will turn my head to now is what I promised to say something about in the beginning. And this is, what does all this mean when we start talking climate neutral economies? And just to show you here, this is the Danish carbon dioxide emission from 1990, where we very often start and UN measure against 1990 as the target year, and then we look until now, and then also in this diagram we look a little bit into the future. And what you can see here is, in the Danish case, and this is similar of course with variations to other countries, is that the energy and transport is really a major part of the carbon dioxide emission and has already been for many years. But this is also the part we have been concentrating on doing something about. And as you can see here in 2020, we have actually achieved significant reductions in the carbon dioxide emissions from energy and transport. This is wind turbines, this is more efficiency, this is all the things we know. But additional to that, we also have agricultural. In Denmark, we have a lot of agriculture. And we have processes from industry and so on and so forth. And all these other sectors also emit greenhouse gases. Maybe not carbon dioxide of all of them, but it's still part of the greenhouse gases. So somehow we will have to align ourselves with those sectors so we can achieve to do it for all sectors, so we can go to this climate neutral and implement those targets. So we did a study. We have done a lot of studies, our research group together with the Danish Society of Engineers starting back in 2006. But recently we did a study where we looked into this, sort of, you can say, updated our studies and related them more to the new political goals. And some of the things we had to ask ourselves is, if we make a study on how Denmark should do the green transition, how should we then look upon Denmark as part of Europe, as part of the world? Because there are so many ways you can do decarbonization and renewable energy. One way is to import ethanol from Brazil, and then that's more or less, then you're dealt with the transport sector. Or you can build a lot of wind turbines and then export them and claim that they are replacing coal-fired power stations somewhere else. But what we said to ourselves and sort of produced a guideline how to think about this is that we said it will not make any sense that one country, no matter if it's Denmark or what country it is, do the green transition if all the other countries are not doing it. Then we might as well forget about it. So this is something we do together, this is something we do parallel. And this means that if we do something in Denmark and we make a strategy on what will be good to do in Denmark, then the overall guideline for this strategy should be that it fits into that all the rest of the countries in the world is doing more or less the same. Of course, there will be differences because we are different, but basically, we should fit into an overall puzzle where we do the same. And defining this guideline is actually quite useful, so I will suggest that to anyone else who's doing a national strategy or municipality strategy or a town, or if it's for Europe or whatever it is, to apply this strategy. It helps you when you then look into some of the details, because the first detail is when we measure, and when the Danish government says, for example, that we'll decrease carbon dioxide emission by 2030, that is our political goal of our parliament and government. When we do this, how should we measure it? And of course, our government measure it the way that UN have told them to measure it. And the way UN measure the carbon dioxide emissions in Denmark is that they do not include international aviation and international shipping. And if we all then apply to that type of accounting, then who should do the international aviation and shipping? So this is the first challenge we have. And what we decided is that we will identify what is the Danish share of international shipping and aviation, and we must include that when we go to the final decarbonized society by 2050. The other issue is that we all know, what about sustainable biomass? What is sustainable biomass? And of course, this is something we debate, and this is moving a little bit in that direction or the other direction. But what we sort of put down as our principle and guideline is that we should do this within our share of what is sustainable biomass in the world. Because there will be countries with more biomass, countries with less, and somehow we need to distribute this. But one important thing about saying this, sort of recognizing that we have some biomass which we can call sustainable and use for the energy sector, and at a certain level we come beyond that, and then it's not sustainable any longer, and so on. But if we do that, then the other side of recognizing this approach is also how much is sustainable and how much is not sustainable also actually depend if you are leading an active policy. And that's what we also recommended in this study to the Danish government, that is to lead an active policy in order to increase the amount of sustainable biomass at the same time as increasing biodiversity. So that's part of this strategy also. Then the next issue is, should we consider ourselves in Denmark an island of electricity consumption and gas and everything, or should we trade with others? And if we trade with others, how should you then understand if we, all of us, by the end of the day, can make this balance in Europe or our neighboring countries, and by the end of the day in the world? And our approach to this is that we sort of look, of course we should trade because there are mutual benefits. There are some very excellent hydropower in Norway that we could all benefit from in Europe. And of course there are also sometimes where we can export some wind and the wind is not blowing so much other places, and PV in the southern and all this sort of thing. So of course we should trade whenever there is a mutual benefit. And we also sort of identified how much that will be. But then beyond that point, there will be situations, if we all do this in Europe, where the wind is not blowing enough, and there will also be situations where the wind is blowing too much. And then our guideline here is then in Denmark, we should make our part of our contribution to be able to solve that, meaning that in Denmark we should have some reserve capacity, our share of what we need in Europe in general when these hours arise. And also we should also have flexibility, and I just mentioned before electrolyzers, for example, which we think is the most doable way of doing it. So these are the principal guidelines, and then we try to apply that to our suggestion on what we could do in Denmark. And first we counted here a little bit just to illustrate it. What does it mean with carbon dioxide emissions? The upper one is how it's defined by UN when we do the accounting in the Danish Parliament for their target of 2030. But then we also included to my side here the fact that in Denmark we actually import biomass. And there are also a carbon dioxide footprint on the biomass we import. But according to UN, that's not our problem. That is the problem of the country where it originated from. But here we just illustrated if that was our problem, because somehow we also have to engage in a dialogue on how we solve that problem. So that is just to illustrate it. But what is really important is when we identified our share of international aviation and shipping, and you can see that to the right there in the orange and blue color, then it really changed the whole picture. Because if we include that, then it's a quite different ball game. Then we really have a much more stronger challenge than is so far recognized by the politicians. So we did a strategy for 2030, and then we also did a strategy for, and we, even though the Danish Parliament have the target of 2050, then we said maybe we can do it a little earlier. So we put on the agenda and we said 2045, just to put that on the agenda. And now we have started a race in the Danish Parliament where we have 12 parties in the Parliament. And some of them then say, maybe we could do it even before that. And so now I have stopped saying, maybe it's also not only a race on how early we can do it, maybe also a little bit to say how we do it. So that's the issue right now. But what we then defined is a full decarbonized Denmark by 2045 in all sectors. And the important part here, when we see how we should collaborate with the other sectors, is that we cannot really see in Denmark that we can bring some of the other sectors to zero. We don't think, we can do a lot within the agricultural sector, but we don't think we can bring it to zero. We think we still will have to produce some cement, and for that reason we cannot bring we have a cement factory in Aalborg, and we don't think we can bring it to zero. Of course, we can replace fossil fuels, but there's still something in the processes with this type of industry and others also. So we don't think we can bring it to zero. The same for flight contrails and whatever. So for that reason, we need something to compensate, and that's what we have as a CCS and biochar. But in our approach, the only reason we have this is to go the last mile. We are not into the business of keep burning fossil fuels and then doing CCS, because we think this is not a proper strategy for the future. But to go the last mile of these other sectors, we think it is something we should do. This is how the Sankey diagram looks, but I would like to look a little bit upon the whole biomass issue. Because as we see it, biomass becomes essential in this process, because if we need somehow to make it possible to make CCS or biochar to provide that sink that can compensate for the other sectors, then we need the biomass. And we have been debating a lot in Denmark. Should we have biomass at all? Is it sustainable? Should we do without it? Our approach from our study is that we should not dismantle biomass. We should further develop it, and we should further develop it in the direction of making sure that it's sustainable, and we should also do actively things so that we can make use of residual resources that is sustainable. And we should also, what is also important, develop it in the way that we use it in the correct way. And this diagram here is our very complicated approach to how we use what we believe we can identify as sustainable biomass in Denmark. And then we use it in various technologies. And the reason why we use it in various technologies is sort of twofold. The one is that all these technologies are not available on a commercial level yet. Not all of them, some of them are, but not all of them. And maybe they will not be commercial within the time rates we have. Maybe they will, maybe they won't. For that reason, it's good to have a combination of many technologies, so if one is failing, then we may be able to use the other. For example, if you look at straws, the way of straws is manifold, and it's both thermal gasification, it's biogas plants, and so on and so forth. That's one reason. The other reason is that that there are strengths and weaknesses of all these technologies. For example, to put straw in biogas, just to mention that one again, a lot of it will come out and not fermented and not usable, but that output could come into pyrolysis, for example, or HTL or other technologies. And by doing it this way, then we can do as it's illustrated here. And the basic principle here is to use the carbon in the biomass and to some extent add hydrogen. So by the end of the day, we get fuels that we can use for aviation and shipping, like methane and methanol, and also simply kerosene for aircraft by the end of the day. And then at the same time, as you can see to the right, we also identify all the point sources we have, both in terms of time and variation and what it will cost to bring them to carbon capture, and also what type it is. And then we identify what do we need for carbon CCU utilization, the circular solution, and what do we have left that we can potentially use for storage and biochar. And by doing it this way, we believe that we can make a scenario that is sustainable in the ways I just mentioned. Time is running, and we should also have time for questions before lunch, so I'll just close very soon, but I'll just mention here that this is where we have really expanded our energy system analysis model. This is to be able to look into this relatively complex issue of dealing with the biomass in a good way. We also published 3 papers about this study here, looking into one of them the overall study, one of them the biomass issue that I mentioned, but also one of them with a focus on the transportation. Okay, I actually have a few more slides, but I think it's better I stop here and make room for some questions.
Thank you very much, Henrik. Okay, time for questions. Wait for the mic to come.
Hi, Shashank Prabhu from Fraunhofer Institute. First of all, thank you very much for really interesting presentation. I wanted to ask you, you specifically mentioned about the electrical grid potential and then district heating potential, which is double to that of the electrical grid, what you have. So in that light, I wanted to ask, have you identified or can you shed some light on distributed energy generation, role of distributed energy generation, maybe in local communities or maybe in some small groups, and with the help of that addressing this issue of both reducing the load on district heating and also maybe increasing the potential of electrical grid. Thank you.
Yes, I can do that, and I can also refer back to the presentation that Nevin Duritz made since already this Monday here. I mean, we look very much at it at the same way as Nevin presented, and that is when we bring all this wind and PV into the energy supply, then we have to build many more than our current electricity demands, because we will have a future electricity demand. But that future additional electricity demand will primarily be for electricity consumption that we can actually stop and go and be flexible about, like heat pump for the heating sector, where we can store the heat, thermal heat, and electrolyzers, as I mentioned a couple of times. And this sort of means that also when we make the distribution on the grid, we can also differentiate between that. And as far as I see it, at least in the Danish circumstances, we will build a lot of offshore wind. And now we're discussing, should we bring it onshore as electricity, or should we bring it onshore as hydrogen? but one way or the other, a lot of it we actually will bring on as electricity for the electricity grid, as you mentioned. But at the same time as we're building a lot of offshore wind in the North Sea, we're also now building a very big ammonia factory out of electrolysis, and you consume a lot of electricity. But we will locate that factory, or it will locate itself, it's private investments, for the same reason, by the shore of where the wind turbines come in at the west coast. Meaning that what we really need there is the cables to bring in the wind, and also, of course, maybe if it's located somewhere else in Denmark, also some transmission lines. But we don't need to bring that to the individual electricity consumers. That will be the distribution grid. And as far as we have been able to see up till now, then if the distribution grid is normal consumers, households like myself with a normal electricity consumption, and in the future an electric car, and maybe some of the households also a heat pump, this is more or less doable within the current distribution grid we have. But the things we are thinking about having, maybe some of you heard my colleague Paul Østergaard make a presentation about the transmission grid in parts of Denmark. What the industry is doing now, there we need to expand substantially our transmission grid and on that level. But the good news is, if you look at the cost of electricity grid, it is the distribution grid that is the expensive one. This is also where we have the losses. So it's good news, as far as I can identify this, that we will not have to really expand that a lot. We'll have to expand it as we usually do, by year and so on, but not a lot. What we'll have to expand is the transmission grid. And that's much more, from a cost point of view, doable. Then there's an issue if people wish to have all those transmission lines going around over their head. That's another issue.
Hello, I am Anna Volkova from Tallinn University of Technology from Estonia. Nice to see you, Henrik. We know each other very good. So, but my question would be, you mentioned bioenergy and biomass, but at least in the Baltic states, we have really a success story that for district heating that it is really high share of biomass boilers and so on. If it is success story, it is a big question, but at the moment this dependence on natural gas is rather small, only for peak boilers we have. So all base loads in Estonia are covered by biomass. But when we study different possibility for waste heat implementation and other renewable low temperature heat sources, they cannot compete with these biomass. So maybe some comments regarding competition. We understand when we compete with fossil fuels, yes, so just CO2 emission savings, very good, good indicators. But when we start comparing, for example, biomass boiler, new biomass boiler installed and replaced by seawater large heat pumps, which use electricity from non-carbon neutral, electricity which is not still neutral, carbon neutral. So in this case, CO2 emission even become higher. Maybe some comments about it. Thank you.
Yes, and first of all, I completely understand what you're doing now and why you're doing it, and congratulations to you that you have no rise in cost because you're not consuming so much natural gas. That's good what you're doing, but I guess my contribution here is, if we look into the future, what is then needful to do in the future, and what do we have to do there? And I reckon that then the price relations will have to change in order for investors to be motivated to do that. But my recommendation to Estonia and other countries will be stop burning the biofuel in boilers and things like that. Put them into thermal gasification or the like, and make gas out of them. Put up some wind turbines and produce some hydrogen. Put that hydrogen together with that carbon from the gasification and produce some methane, methanol, whatever that we will need for the transport sector. And then while doing that, there will be a lot of waste heat from the electrolyzers and also the thermal gasification or other technologies to do the same and use that for district heating. That will be my advice for the future. I reckon that of course will take some changes. We did actually a study that we call smart energy markets, where we sort of were taking the same smart energy systems approach, just taking on the energy markets, because they are also correlated. With all this electrolyzers buying electricity, dealing with the other markets, I mean, they should also be somehow coordinated. And I think it's obvious that we'll have to reorganize both our electricity markets gradually, as we already have been doing many times, and we should do that also. And when I look to the future, already before the crisis, it's obvious that the natural gas price is too low for the future. We cannot make the future work as low as the natural gas used to be. Then now it's way too high. But somewhere in between that should settle on a level that will make us not burn natural gas in boilers, that will make us use natural gas for transportation and others issues. So when we look to the future, there will be power stations on biomethane. So that's my answer to you, Anna.
One final question, if there is.
How do you see international shipping and aviation going to which fuels? And also feedstock for chemical industry?
What we have been doing there is that, first of all, we have been allocating, I'm not so sure it's in this study I just presented it, but in previous studies we allocate a part of it for materials to replace plastic and whatever. That is the way we deal with that. The other things, there is a paper here that is looking into the details of the transportation, but when it comes to aviation and shipping, we think shipping will be a combination of ammonia and methanol. That's how we produce it in this here. And then of course
not
electric ferries.
Not the e-LNG. You don't see it in the long distance shipping.
We have not included it in this study here, but
okay.
We're very open to see if there are better options. And then for aviation, it's simply jet fuel that we upgrade the methanol and whatever to jet fuel. There's been a lot of talk about hydrogen planes and so on. I cannot see for myself that we can replace the fleet in the world for hydrogen, as long as we can't even buy them as we speak. So I think the doable way is to produce green kerosene. And then of course we can discuss if we should fly as much, and also what level of altitude we fly at, because this also means a lot to the flight controls, and we also have advocated measures in such respect. But that's basically what we have in the study here. But we're very open to other suggestions as well, of course. And I mean, if we look at ourselves, not in the aviation and shipping, but in the heavy-duty trucks, when we did the same type of studies 5-10 years ago, we were not very optimistic regarding trucks and buses and so on. But now we're much more optimistic about that. For example, in Aalborg just bought 110 buses for the urban areas, and they are all electric buses. So all buses in Aalborg now is electric buses. And then we also have a few hydrogen buses, but they are running out of business because they are so less efficient than the electric bus as it is now.
Okay, I think one last one, okay, because it's already 12:30. So a quick answer, please.
Okay, just one question. The energy transition in Denmark was quite successful. So, can you go a little bit to the history, and say who will be the major stakeholders that will bring this fully decarbonized Denmark? Because you had the union workers that were promoting renewable energy, then society of engineers, and maybe industry. But in your opinion, how it will work in the future? Who are the key stakeholders, or who will make the major role?
Soteris just told me to have a short answer.
Yeah, it's
to
a long story, I guess,
to the long
to
story.
reply.
That's sort of a challenge. But let me put it short in the way that I disregard the story and just look at where we are right now. And where we are right now is that all the things I talk about here is things that should be implemented, most of it by private investors. And just before I came here, I think a week ago or something, the Danish power company Ørsted and another company called Copenhagen Infrastructure Partners announced that they are going to build a 5.2 gigawatt of offshore wind. 5.2 gigawatt of offshore wind, and that's a lot, with no subsidies, and they claimed it will be ready to produce in 27. That is a lot of wind power built. And the same company, Copenhagen Infrastructures, are investing in that factory and are well long in the process of doing that I mentioned before, that will produce ammonium. All municipalities in Denmark are having negotiations with investors in Power to X, and this is facilitated by the government and so on. So this is a hand in hand where the government facilitate, sometimes by subsidies, and now subsidies is not needed any longer than by other types of support, and then private investors is doing this. In the last competition of building on a tender an offshore wind farm in Denmark, a lot of companies were giving, putting in tenders how much they needed in subsidy, and all of the bidders, and there were several of them, they said zero. We need zero in subsidy, and so they couldn't decide who should win. So they had to draw a law, and then a German company won. And that's why the two Danish companies was a little angry, and now they are building a lot without subsidies as well under another. That's a long story. but this is happening with private investors as it is now, most of it.
Okay, thanks a lot. Thanks again, Henrik, for your interesting presentation. Now is the lunch break, so enjoy your lunch and come back on time for the rest of the sessions.